Hello friends, welcome to part 4 Mechanics paper 2019 solution paper C2 of physics honors for BSc first sem, and we're gonna start from question number 5C. Okay, so up to question number 5B we have already solved from part 1 to part 3. I have provided the links of those videos in the description box. So now let's start, and before we start, please subscribe the channel if you are new to my channel, and like and share. Also hit the bell icon so that you get notified when new video will be uploaded. So this is gonna be the last video of this paper. So from the next video I'm gonna solve mechanics paper 2021, right? So now let's start. So this is the question number 5C. Here derive an expression for the gravitational potential and gravitational field due to a spherical cell of radius r of mass capital M at any distance r from its center, where r is greater than small r is greater than capital R, right? So here you see, we know that gravitational attraction force, that Fg at a point due to a particle of mass capital M at a distance of r. So it is at a distance of r from the point, is in accordance with Newton's law, is given by Fg is equal to minus capital G capital M by r square r cap. So this is the expression, Fg minus capital G capital M by r square r cap, where r cap is equal to this is unit vector of r, that is given by r vector divided by magnitude of r, is the unit vector along r, right? So where r cap is the unit vector along r. So thus the force per unit mass is the measure of the field intensity. Now you see the work done moving a unit mass from infinite to any point in the gravitational field of a body is called a gravitational potential at that point due to the body. Now gravitational potential at a point in a gravitational field may also be defined as the potential energy of the unit mass placed at that point. So it is usually denoted by Vg, right? V small g, right? So its value at a distance r. So where r is written bold, you will write r vector. Okay, so in books I have just clicked a photo from books. So if you see, sometimes in books they don't used to write this arrow symbol, rather using arrow they used to make it bold, right? They used to make it bold like this. Okay, if you see that where the letter is bold, where the alphabet is bold, then it means this is a vector. Okay, write this way, vector symbol. So hope you have understood this. Now you see, so that gravitational potential, that Vg, is given by integration from infinity to r Fg dot dr vector, right? So this is the expression. Let me write here. So Vg is equal to minus integration from infinity to r Fg dot dr vector. You should write this way, and this is negative sign here, you can see. So now you see, this Fg is nothing but it is equal to minus capital G capital M by r square r cap. So you can replace this Fg with this result, right? And if you do so, and if you simplify, integrating and all, here you will get the final result, that this is the final result, right? So this is the expression for gravitational potential, right? So this is the required expression that finally we have got after doing simplification, integration and all. So what we have got, Vg is equal to minus capital G capital M by r. That's what we have got, right? So hope you have understood this. So now you see, because you see we are solving question paper, so we will not concentrate in explanation in details. Okay, so now let's move on to next part of the question. Here you see, so let me clean this. So here you see the gravitational field due to a spherical cell of radius capital R. The answer I have taken from the book. Here you see, so here in this book they have taken the radius of the sphere is a, right? So in the question you were asked to take r rather taking a, so that's why you just replace this small a by capital R. Replace this small a by capital R wherever small a is used, just replace it by capital R, because in the question it is mentioned that radius of the sphere is capital R, but the book from which I have taken this photo of this answer to this question, they are using small a. That is the only difference. So just you change the term by small a by capital A, right? And that's gonna be all fine, right? So here you see, so let us consider a uniformly dense spherical cell. We have taken, I have drawn the diagram here, you can see dense spherical cell whose thickness is small, very small compared to the radius. So the thickness of the cell, you see, thickness of the cell is very less compared to the radius, right? So radius we should take here capital R. So let O be the center of the spherical cell and small a is its radius written, so let us replace this small a by capital R. So let me write it capital R. So here also in the diagram let me make it capital R. Okay, so and let P be a point at a distance r from the center O where the potential has to be found. So this is the point P here, you can see, which is at a distance of r from the center O. At this point we need to find the potential, right? Now you see, let the cell be divided into a large number of thin circular rings. So this is the cell, suppose. So let us divide it by very large number of large number of strips. I have divided it into very large number of rings of very small thickness. Okay, very thin rings. Okay, so here you see, let us take one ring here. This, see the diagram, this is the ring I have taken here, you can see. So such that A, B, D, C, so its thickness is very small, and the angle AOC, here you see, so this is the ring, right? A, this is C, suppose, and this is the center. This angle AOC is very small angle, this is D theta, right? This is D theta. So hope you have understood from the diagram, right? So now you see, so these rings are taken in such a way that here you see, these rings are planes perpendicular to OP. So we have taken the rings in such a way that they are perpendicular to OP, right? So we have assumed that way, right? So now you see, let us consider one such ring lying between the planes AB and CD. So these are the two planes AB and CD. Here you can see the diagram. This is A, B, C, D on the right hand side, right? So between these two planes we have taken a ring. It will obviously be a ring of thickness AC. So thickness of this ring AC is given by r d theta. Okay, so here let us replace this small r by capital R, small a by capital R. So as we are taking as in the question it is given that the sphere is of radius capital R, so AC will be taken as capital R dot d theta, capital R into d theta, right? capital R into d theta. So you know that this is a circle. Suppose if radius is r, so and the angle made by an arc at the center is suppose d theta, it is in radian, then the length of the arc is given by r d theta. So using that concept, so I have found a thickness of this ring. So hope you have understood this. Now you see the radius CE. So here you see this is the center of the ring. This point E represents the center of the ring. If you see this diagram or that diagram, doesn't matter, same both are, but as this is very small, so I have drawn here. So this point E is the center of this ring, circular ring. I have assumed here, right? So then CE will be given by though I have here it is written a sine theta, so rather writing write CE r sine theta. Just replace the small a by capital R, right? So replace this small a by capital R. So in each and every terms where you have got small a, just replace it by capital R. So here you can see, if you see this result, you have 2 pi a instead of a, write capital R sine theta cross r d theta, right? So mass of the ring, so this is the area of the ring, right? Circumference and thickness. This is circumference into thickness. So this is the circumference of the ring and this is the thickness, that gives the area of the ring, right? And if you multiply the area with the density of this cell, then you will get the mass, right? So this is the density here, sigma, and let me write the expression in terms of capital R, right? So let me write this result in terms of capital R. So that's gonna be 2 pi capital R sine theta cross, let me clean this one, cross r d theta into sigma, which represents the density, right? So you see whose thickness, let me just mention here. If the meaning of this sigma is not mentioned anywhere, just mention it here. So let us consider a uniformly dense, let us write within bracket sigma here, dense spherical cell, density is sigma here, okay? So mass of the ring that we can write, if you multiply this capital R and capital R, you will get capital R square, and that is why we have got this result 2 pi a square. Instead of a square you have to write capital R square, right? So this expression gonna be equal to, so let me rewrite this expression. So this is gonna be capital R, right? 2 pi capital R sigma sine theta d theta. That's what we're gonna get, right? So just let me write it properly. So just replace this result by this result. So I have written in terms of capital R, rather writing a, okay? So similarly this line can, just you replace this line by this one. So 2 pi capital R sine theta into r d theta into sigma, and the last line, that mass of the ring, rather writing this one, just write 2 pi r square sigma sine theta d theta. So hope you have understood this. Just I have written the same lines in terms of capital R, because according to the question, the radius of this sphere is capital R, not small a, right? So now we have considered that CP, this length CP is small x. Let me write this one as small x. Every point of the ring is at the same distance. That means all the point, each and every point on this ring here, you can see on this ring are equidistant from this point P, right? All are at a distance of x, right? Now you see Therefore, potential at P due to the small ring is given by dV minus capital G. Then here you have to write the mass of the ring, and here you have to write the x, that is distance of the point from this ring. So this expression, if you write in terms of capital R, it will be like this: 2 pi capital R square sigma sine theta d theta by x. So this is suppose equation number 1. So this is equation number 1. So now let's move on to the next slide. So now in the triangle COP, if you take the triangle COP, this one, let me go to the next slide. So here you see, so we are going to consider triangle COP, right? So this triangle, so let me make the small a as R. So if you take this triangle COP, this is COP, and here you have the perpendicular E, right? So this distance is small r, and this is x, right? This is x, and this line will be capital R, right? OC will be capital R. So if you apply here cosine law, that means if you see, just simply here you can see, first take this triangle. If you take this triangle first, then what you will get from this triangle, if this is 90, from this part you will get that x square is equal to CE square plus EP square according to Pythagoras theorem, right? EP square. Then CE, if you apply trigonometry, this angle is theta, then you will get this one as capital R sine square, capital R square sine square theta, and EP, this part EP, it can be written as OP minus OE whole square. So OP minus OE whole square, right? So you can write OP minus OE square, and OE can be written as R cos theta. R cos theta. From this triangle OCE, you can write OE is equal to R cos theta. And if you put if you replace OE by, if you replace this OE by R sin theta, and if you apply here a minus b whole square formula, and if you simplify, then you will get this result. Here you see. So let me write this one in terms of capital R, that is x square is equal to capital R square plus small r square minus 2 capital R small r cos theta. You will get this result. So let me write it clearly. So this is going to be equal to x square is equal to capital R square plus small r square minus 2 capital R small r cos theta. So that's going to be our result. If you simplify, you don't have to show these things, just note as it is given in the book, right? So now you see, now if you differentiate this above equation, then you will get this result. So here you see, let me write this one in terms of capital R. So that's going to be twice x dx is equal to 2 capital R small r sin theta d theta, sin theta d theta, right? Let me write here sin 2 capital R small r sin theta d theta, right? So you will get this, and this implies this result. So here the denominator will be capital R small r. Rather writing a, just write this, just let me write here. So simplifying this, you have got sin theta d theta is equal to 2 cancels on both sides, x dx by capital R small r. You will get this, right? So if you substitute this value in equation number 1, so let me go to previous slide. What was the equation number 1? This is the equation number 1. So if you put this put the result you have got here, this result sin theta d theta, here if you put value of sin theta d theta in this equation, then it gonna give you this result. Here you see dv is equal to this one, right? So if you write this result in terms of capital R, so instead of using small a as given in the question, the radius is capital R, so just replace this a small a by capital R. So can you see this expression here? You see this small a should be replaced by capital R, and if you do so, then what you're gonna have here, not only this small a, here also we have small a square. So just let me write the expression here. So your dv will be equal to minus capital G 2 pi capital R square sigma x dx divided by x capital R small r. So here you see this small capital R cancels R square, capital R square, and finally we have got this result, minus G 2 pi capital R sigma by small r. That's what we will get, because this x also cancel here, right? So hope you have understood this. So let me write this dv clearly. So what I have got here, dv is equal to minus G 2 pi capital R square sigma x dx, right? Sigma x dx. Divided by x capital R small r, right? So this result implies gives this one. This is equation number 2 we have taken. Now actually there are 3 cases. This p may be lying on this surface and inside the surface. So but in the question we are going to answer, we are going to find the expression for the gravitational potential for this p which is outside the cell, right? So in upcoming exams, so you may be asked for the same expression if the p is on the cell or inside the cell. So read those topics also, right? So just I am giving the answer what is asked in this question. So here you see, when p is outside a cell, here you see it is given in the question. If you check the question, that small r is greater than capital R, right? So small r is the distance of this point p at which we need to find a gravitational field, and the capital R is the radius of the sphere. So small r is greater than capital R, then p must be lying outside, right? So hope you have understood this. So here you see this dv is integrated now. This dv is integrated from r minus a, actually it should be r minus capital R, right, to small r plus capital R. That means here you see this diagram, if you check this diagram, this is capital R, right? So we are going to integrate from this point k, to the point L, right? So because we are going to find a potential for all the due to all the rings, so that I have divided this sphere into large number of rings, right? So to find that potential for all the rings that I have divided into the cell. So here you see, so this distance from the point P, this distance is capital R, right? So this distance is small r, so this is r plus r, small r plus capital R, and this distance L, from P to L, this distance is small r minus capital R, and this distance K to P, this is what small r plus capital R. That's why we need to integrate from v is equal to integration from small r minus capital R to small r plus capital R, and here you will get minus z 2 pi capital R sigma by small r dx, right? You will get this expression. So if you integrate this, then you will get this result, right? So just replace the small a by capital R in its expression, right? So your final result will be minus z dot 4 pi capital R square sigma by small r. So this result you will get after integration and putting those limits r plus capital R and r minus capital R. So if you replace this a by capital R, right? So just you make you change yourself wherever it should be changed, right? So now 4 pi a square, though you here it is written 4 pi a square, you write 4 pi capital R square, right? Is the surface area of the whole cell, and hence surface area into the density. The sigma is the density, so 4 pi capital R square into sigma, that's gonna give you the mass of this cell, capital M. So we have taken the mass is capital M, and this is suppose equation number 3, right? It is the same as it would be due to the mass M placed at O, right? So thus the spherical cell for external points acts as if all its mass were concentrated at its center. So that means here you see the spherical cell for external point, for the point which is outside the sphere, that means they are talking about this point P which is outside the cell. So for it that means all masses of the cell are concentrated, all mass of the cell is concentrated at the center. You can consider that way. The gravitational attraction or gravitational field at this point P is negative of the potential gradient at that point, and hence the attraction at P or gravitational field at P in this case will be F is equal to minus dV by dr, right? And if you put the value of V here, if you put V is equal to minus Z by capital M by small r, that is if you use equation number 3 here, then what you will get at the end, you will get this expression F is equal to you will get F is equal to minus Z capital M by r small r square, and let us suppose this is equation number 4, and instead of a unit mass, a point mass M is placed at the point. So we have considered now that a point of mass M is placed, small m is placed at this point, right? Then the field or the gravitational attraction force will be given by capital F, this capital F is equal to minus capital G capital M small m by small r square. So this is the required expression. So hope you have understood. So now let's move on to next exercise and next question. So this is also question number 5C. So there were two questions. The first one that we have already solved, or this one, okay? So you have to solve any one, though I have shown both here. A rocket starts vertically upward with a speed of v naught. So a rocket, there is a rocket that is going upward. It is going upward with velocity v naught, right? So that the speed v at a height h is given by, so its speed at speed v after it reaches a height h from the earth is related by this expression, this relation. So where capital R is the radius of the earth, so radius of the earth is capital R they are taking, and small g is the acceleration due to gravity, right? So kinetic energy of the rocket at the earth surface will be, we know kinetic energy is given by half mv square, and when the rocket is just released, just launched, so at that time v naught was the velocity, right? Initial velocity, so half mv square, and the potential energy of the rocket at the earth surface will be given by minus capital G capital M small m by r square, where small m is the mass of the rocket, mass of the rocket, right? And capital M is the mass of the earth. Capital M is mass of the earth, mass of the earth, right? So potential energy of the rocket at the height h will be given by minus g m small m by r plus h. Why r plus h? Let me tell you. So this is the radius of the earth, capital R, right? And it is at a height h. So total distance from the center of the earth to that point. So already I have told you that if you put a mass here and for a external point, so we will consider all mass of this sphere, that means in this case earth will be concentrated at the center, so that's why we have to take the radius with the height as well. So that is the potential given by this expression, capital G is capital M small m by r plus h. So this should be negative, right? So now by the conservation of energy, law of conservation of energy, we get this relation, total energy remains constant, right? So, and if you simplify this equation, then you will get this, get the required relation that asked in this question. So hope you have understood this. So it's very simple. Now let's move on to next question, that is a frame of reference. This is question number 5D. A frame of reference rotates with the angular velocity omega. Omega is the angular velocity of a frame. So you can see there are two frames. One is what? X, Y, Z. So there is another frame that is rotating with angular velocity, that is omega, that is x dash, y dash, and z dash, right? You can see the figure, right? So now you see you have a point here P whose position vector is r vector here. So they are writing here, you see bold r, that means this is r vector, right? So remember that. So this is with respect to the initial frame, that is initial coordinate system, that is x, y, z, and this is with respect to x dash, y dash, z dash, position vector of the same point with two different frames. So hope you have understood this. Now an observer in the system S dash situated at the origin will observe the time derivative of this r vector, position vector 2b. Let me go to next slide. 2b, this is the time derivative, okay, for the observer which is at the center origin of S dash, and but the time derivative for this r vector relative to the observer in the system S will be given by this, and this is suppose equation number 2, and this one is equation number 1, suppose. So here this is r vector, where you have seen bold r, that is r vector, remember that, okay? So these are the unit vectors I dash, z dash, k dash for the rotating system, right? And these unit vectors are rotating with a uniform angular velocity, that is omega. So we have the time derivatives, these are, and this is along x-axis, x dash, this is along y dash, this is along z dash, right? So similarly for the system relative to the system S dash, we're gonna write the derivatives as this way, d dash by dt, right, instead of writing d by dt, okay? So that is what we have done here. Here you can see d dash by dt of r vector is given by dx dash by dt dy dash by dt. So let me write it cleanly so that you can recognize. So d dash r by dt is equal to dx dash by dt I cap, here I dash, okay, unit vector I dash. So dy dash by dt, so z dash, then plus dz dash by dt. This is k dash, this is k dash. This is equation number 4, right? This is the equation number 4, right? So where the differential referred to as dash is denoted by, as I have already told you, that d dash by dt, and this represents the velocity of the particle relative to s dash. So we know this r is position vector, then its derivative represents velocity, and if you take d dash by dt, then it will represent velocity with respect to this s dash. So hope you got this. Now in view of 3 and 4, equation number 2 may be written as this equation number 2, that where is the 2? So this is the equation number 2. So we have got here dx dash by dt, dy dash by dt, dz dash by dt. So then plus we have got x dash di dash by dt, y dash dy by dz by dash by dt, then z dash dk dash by dt. So here it can be replaced. So by, you can see we have already got di dash by dt omega into I dash, omega cross I dash. So similarly dz dash by z dash by dt, we have got omega cross z dash. So from this equation number 3 and equation number 4, if you used in equation number 2, in this equation number 2, using 3 and 4 into, we have got this relation, right? And this can be simplified as this, right? So here you will get, you can take this common, right? Omega cross, you can write like this, omega cross, that is r dash x dash r dash, y dash z dash, this is z dash k dash, you can write this. So I think there is a printing mistake here, so it should be, rather writing r dash, so this should be I dash, I think, right? So let me rewrite this relation, it is printing mistake here. So d dash by r vector, d dash by dt of r vector is given plus omega, this is nothing but dr vector by dt, that's gonna be equal to d dash r vector by dt omega cross, omega vector cross x dash I cap. They have written r dash instead of that, so that's wrong, okay? So be careful. Then y dash j dash, then plus z dash k dash. So this is the correct expression. So there was a printing mistake. So now this vector, this is x dash I dash plus y dash z dash plus z dash, this is nothing but your r dash vector, this is r dash vector. So omega cross r dash they have written, right? So from the above, the operators d by dt and d dash by dt are related by this relation, d by dt. So let me write the relation here. We have got this relation, d by dt is equal to d dash by dt plus omega. Actually this is not actually x, this is cross. So what we have done here, you see, from this relation, if you remove this r vector from this relation, this relation will be obtained. If you remove this r vector from that this equation number 5, from this equation number 5, if you remove the r vector, then you will get this relation. And this is nothing but this is not x, this is cross, right? So this is the required relation equation that we are asked to find. So here now let's move on to next question. Here you see this is our next question. Calculate the magnitude and direction of Coriolis acceleration of a rocket moving with a velocity 2 km. I have a doubt here. Here you see this direction of the linear velocity is not clearly mentioned here, 2 km per second is given, but not it is going towards south or in which way it is not given, but altitude is given, latitude is given, that is 60 degrees south. So here I have assumed this is moving in south direction, towards south. Okay, towards south I have considered that way, the linear velocity, direction of the linear velocity. So now you see, if you do so, now the magnitude of Coriolis acceleration is given by this formula, right? So put the value of v and the angular velocity omega, so you will get this result. So this is in meter per second square. First convert this one kilometer per second to meter per second, right? So then we have got this magnitude and two direction. Now you see the Coriolis acceleration in vector form, it is given by AC vector 2 omega cross v. So this omega vector, if you write this one in vector form, so here you will get omega cos 60 j cap omega sin 60 k cap, where latitude is 60. So we know that j cross j, if you find omega cross v, j cross j, that's going to be 0, right? And j cross k, sorry, not j cross k, so k cross j, as we are going to find here omega cross v, so then k cap cross j cap, that's going to give you minus I cap. So I is in this direction east, right? So that's so minus I will be towards west, right? So along west, that's going to be the answer, right? Now let's move on to next question. At what speed a particle will be moving if the mass is equal to 3 times its rest mass? So v is the supposed required velocity of the particle we have considered, and m be the mass of the particle, right? And m is equal to thrice m naught. So m naught is rest mass. Okay, m naught is rest mass. So it is given that its mass is equal to 3 times of its rest mass. Okay, it is given in the question already, right? So that's why we are using here m is equal to 3 times of f naught, right? So you have already got this relation, m is equal to m naught divided by root over 1 minus v square by c square, right? So here if you simplify this, you will get this m naught by m is equal to root over 1 minus v square by c square. So we know this m is nothing but 3 times of m naught, so we have used that relation, equation number 1 in this equation. Then m naught cancels, so we have got 1 by 3 is equal to this. So squaring both sides, we have squared here, so this square root is removed, right? So now putting the values here, you see values of c, if you put the value of c here and if you simplify this, then you can find the v, velocity of the particle, and this is the answer we have got. Okay, so hope you will understand these calculations, right? Very simple. So that's how we can solve this problem. So now let's move on to the next question. Here the calculate the wavelength of gamma ray photon produced in 2/4 means half annihilation of an electron and positron. If electron and positron, they during annihilation of these two, actually two gamma photon are released, but 2/4 means half annihilation, so there will be one gamma photon, right? So that's why we have taken this relation, energy of this photon will be half of the total energy that produce an annihilation of this positron and electron, right? So using that operation, here we have got this data that mass of the electron and protons same, mass of both same, and velocity of light is given here, value of h is given. So use this relation, and if you put the given values here, then if you calculate, you will get the wavelength. This is the wavelength of the gamma ray photon released in this phenomena. So this is the required wavelength of the gamma ray photon. So hope you have understood this. So now let's move on to next. So deduce an expression for relativistic variation of mass with velocity. So this topic I have already made a video on this topic. If you go to the relativity playlist, so just do one thing, just check the description box. There I have given the link that I have written there, relativistic variation of mass with velocity. Then I have given the link, right? So there, so if you visit that link, you will get the answer. You can directly you can write the answer directly from that video, right? Now let's move on to so our next question here: deduce a mathematical expression for the law of addition of velocity, right? So that means relativistic law of vector addition of velocity. So here you see, suppose we have considered two frames S and S dash. These are two frames S and X dash. Okay. So S and S dash, their origin respectively are O and O dash. Okay. Suppose we have a particle here P, and it's moving with velocity U with respect to the frame S, and U dash with respect to the S dash, and this frame S dash moving along x-axis with constant velocity v, suppose. So let me write here what we have considered here. So now u be the velocity of the particle with coordinate x, y, z with respect to S, and same thing for the particle with respect to the frame S dash, right? So now you see what will be the by Lorentz transformation. You see, by the Lorentz transformation, we have got x dash is equal to this equation number 1, and as the frames are moving along x-axis, so y dash and z dash remain same as y and z, right? And velocity of the particle p with respect to this S frame is u is equal to dx by dt, and with respect to S dash you can write u dash is equal to dx dash by dt dash, right? So, and here you see what you can do, and by Lorentz transformation you will get t dash is equal to t minus x v by c square divided by root over 1 minus v square by c square. That's what you will get. This is suppose equation number 2. So here is equation number 1. Let me write it properly. So this is equation number 1 and this is equation number 2. So what are we going to do now? Now let us differentiate these two equations, equation number 1 and equation number 2. So let me write this two on the other side, on the other slide. So first let us differentiate equation number 1. Differentiating equation number 1. So dx dash will be, and here you see you will get dx v dt. Here v is constant velocity, so if you differentiate you will get this. Then here 1 minus v square by c square, you're gonna get this, the derivative of this first part, and differentiation of this equation number 2. Equation number 2, you will get dt this is equal to dt minus dxv, or you can write v dx by c square by root over 1 minus v square by c square. That's what you will get. Now let's find dx dash by dt, right? Let us find it, dx by dt dash, right? dt dash. So that means divide this one by this, then what you will get, then denominators will be cancelled, this denominator will be cancelled with this one, then you're gonna get, and we will get dx minus v dt divided by dt minus v dx by c square. That's what we will get, right? So what will be the next step? If you divide both the numerator and denominator by dt, then you will get dividing both the numerator. So instead of writing sentence so like this, just divide both the numerator and denominator by dt minus b. So dt will be cancelled here, minus b you will get, and here 1, then b by c square, then dx by dt. That's what you will get. So you know dx by dt is nothing but u, right? That velocity of the particle. So what we will get, and dx dash by dt is u dash, right? So here you can write u dash u minus v by 1 minus u v by c square, right? So that is what you can write. This is the velocity of the particle with respect to, this is the velocity of the particle relative to or with respect to the frame S, this, right? So now let us find a velocity. If you want to find the velocity of the particle with respect to s dash, sorry, not s dash, s, then just replace the u dash by u and u by u dash, then what you will get, u will be equal to u dash, then if you, then this sign will be changed, that will be plus v by 1 plus u dash v by c square. That's what you will get. So this is the relativistic law of addition of velocity, right? So what you can write, relativistic addition, relativistic law of addition of velocities, right? So now let's move on to next question, the last question of this paper. So then from tomorrow I'm going to upload solutions of C2 paper, mechanics paper of BSc first sem 2021, right? So let's complete the last one. So here you see a rocket is moving with a speed of 0.9 c with respect to the earth. So this rocket is moving with respect to the earth, one rocket is moving with respect to earth with the speed 0.9 c. Okay, so let me take this one as v1, let me take this one as v1, and this is the, suppose earth is your frame of reference S, and this is the frame of reference S this, right? So another rocket we have, so it cross that this is the, you can consider that particle. So as here recently we have solved the previous problem that we have discussed about the relativistic law of addition of vector. According to that, so you can consider earth as S, frame of reference S, and S this as the first rocket, and the next rocket you can consider the particle P, which is moving with velocity v, right? So which is moving with velocity v, suppose, and the velocity of this particle with respect to this S this, right, which with respect to S dash is V2. So you can replace the U dash by V2. You can consider instead of U dash as V2, right? So this is the second rocket and this is the first rocket, right? So V2, so here V2 is the speed of this second rocket with respect to the first rocket, right? So this is 0.4. Now we have used the relativistic law of vector addition, right? Relativistic law of vector addition. How? Let me tell you. So here, as you see in the previous question that we have discussed, that two frames we have taken, that we had taken S and S dash, S and S dash, right? And a particle we had considered here, which was moving with U with respect to S and U dash with respect to S dash, right? So, and S was moving with V, and S dash was moving with constant velocity V. In that case, with respect to S, the velocity of this particle P was obtained by this relation that U is equal to U dash plus V by 1 plus U dash V by C square, right? So now, in this case, this U dash is, we have taken V2, and U, that sorry, not U, the V that the V that first rocket we have taken as S dash, that V is taken here, this is 0.9 C, right? V is 0.9 C. Then the we need to find the velocity of the second rocket. This particle P is considered as second rocket, so which is moving with velocity U with respect to S. So in this problem we had taken this one as V, right? We have taken this one as V. So applying the relativistic law of vector addition, so we have got this relation, and putting those values we have got here, and we have got this answer. So this is the answer, right? So hope you have understood. That's how we can solve this problem. And thank you for watching. See you in the next video. Please subscribe the channel if you are new my channel, and if you like my videos, do share with your friends and hit the thumbs up button, and also hit the bell icon so that you get notified when the solutions of next paper will be uploaded. So see you in the next video. Thank you for watching.